Welcome to the course Nuclear and Particle Physics. Course code BSCP3051, program name BSc Honors Physics. Our topic of discussion is Semi-Empirical Mass Formula. I will cover the topics calculation of binding energy with semi-empirical mass formula. Here volume energy term, surface energy term, Coulomb energy term, asymmetry energy term, pairing energy term we will discuss. We will see some examples to calculate binding energy. As a prerequisite, we should have the knowledge of constituents of nuclei, knowledge of binding energy and liquid drop model. The objective, after studying this unit, we will be able to know the binding energy with the help of semi-empirical mass formula. Introduction. In nuclear physics, the semi-empirical mass formula is also called Weizsäcker's formula or Bethe-Weizsäcker formula. This is used to approximate the mass and various other properties of an atomic nucleus from its number of protons and neutrons. It is based partly on the theory and partly on empirical measurements. The theory is based on liquid proposed by George Gamow, which can account for most of the terms in the formula and gives rough estimates for the values of the coefficients. It was first formulated in 1935 by German physicist Carl Friedrich, and although refinements have been made to the coefficients over the years, the structure of the formula remains the same. The analogy between nucleus and liquid drop has been used to set up this semi-empirical formula for mass or binding energy of a nucleus in its ground state. The formula has been obtained by considering different factors of the nucleus binding. The mass of the nucleus can be expressed in terms of the total binding energy B. Now we will see how we can calculate binding energy with semi-empirical mass formula. There are 5 energy terms. First one, volume energy term denoted by B1, surface energy term B2, Coulomb energy term B3, asymmetry energy term B4, pairing energy term B5. Asymmetry energy and pairing energy are the correction terms based on quantum effects. So total binding energy will be the summation of all these 5 energy terms. The first 3 main terms in semi-empirical mass formula are based on liquid drop model. Now we will discuss about volume energy term B1. The volume energy term arises from the interaction of the nucleons through the strong force. When an assembly of nucleons of the same size is packed together into the smallest volume, each interior nucleon has a certain number of other nucleons. In contact, energy is proportional to volume and is found fairly constant for stable drop nuclei. Now volume energy term B1 is proportional to A. Now we can take the proportionality constant as AV, which can be evaluated using experimental binding energies of nuclei. The plus sign indicates the binding effect of the attractive forces. Here we can see the graph, volume energy term versus atomic mass. This graph shows the variation of binding energy per nucleon with atomic mass of volume term. It is constant because the strong nuclear force between the nucleons has a limited range and a given nucleon may only interact with its direct neighbors. Now we will discuss about the surface energy term V2. Surface energy term takes into account of nucleon at the surface of a nucleus that interacts with fewer other nucleons than one in the interior of the nucleus. Hence, its binding energy is very less. It is proportional to the surface area of the spherical nucleus. The surface term is also based on the strong force. It is a correction to the volume term. So V2 is proportional to minus 4 pi r square. Negative sign indicates that the volume energy term overestimates the attractive forces of the surface nucleons. Now we know that r, radius of the nucleus, is equal to r naught a to the power 1/3. So we can use this r into the expression of V2 and V2 becomes equal to minus 4 pi r naught square a to the power 2/3 is equal to minus as a to the power 2/3. As is the proportionality constant and is evaluated using experimental binding energies of the nuclei. Now the graph it is shown over here. The binding energy per nucleon, it is in y-axis, and atomic mass for surface energy, it is given over here. We can see that how the graph varies for surface energy term. Now we will discuss about the Coulomb energy term V3. It represents the energy incorporated in the nucleus due to the positive charge proton present in the nucleus. This is only long range force in the nucleus. This arises due to Coulomb repulsion between the protons. This term is of the form V3 is equal to minus AC Z minus 1 a to the power minus 1/3. This proportionality constant AC can be evaluated using experimental binding energies of nuclei. So binding energy per mass number A is equal to minus AC Z minus 1 a to the power minus 4/3. The graph shows the variation of binding energy per nucleon with the atomic mass for Coulomb energy term. This Coulomb energy term lowers the binding energy because of the repulsion between the charges of equal sign. So total energy term, which comprises of V1 plus V2 plus V3. So we'll get binding energy per nucleon BE by A is equal to AV minus AS a to the power 1/3 minus AC Z minus 1 a to the power minus 4/3. Here in the graph we will see that volume energy term which is constant with mass number, then volume plus surface energy term which is varying like this, and the third one volume plus surface plus Coulomb term. So we can see the basic shape of the curve matches the experimental curve for the binding energy per nucleon. Now we will see asymmetry energy term V4. This is taking into account of two effects based on quantum mechanics that are not explained by simple liquid drop model. Asymmetry energy term reflects the stability of nuclei with the proton and neutron numbers being approximately equal. B4 is equal to minus AA, which is the proportionality constant, A minus 2Z whole square by A, where A is the mass number. Empirically, AA is equal to 23.21 mega electron volt. This term depends on the neutron excess minus Z in the nucleus, and it decreases with the increasing nuclear binding energy. The correction term is needed due to the occupancy of neutrons in the higher energy levels when N greater than Z as compared to the lighter nuclei when N and Z are equal. For heavier nuclei, the Coulomb repulsion effect starts showing up, and to compensate for that, N becomes greater than Z and the nuclear force becomes less effective. The next energy term is pairing energy term. This is also a correction term. Pairing energy term is for the tendency of proton pairs and neutron pairs to occur. As even number of particles is more stable than odd number due to spin coupling, so this term is incorporated. All the terms in the binding energy having a smooth variation with respect to N or Z or A. However, in the actual binding energy versus mass number curve, there are several discontinuities. From the pattern of abundance of stable nuclei, it is seen that even nuclides are more stable than odd even odd, or odd nuclides. Odd nuclei have very low binding energy due to the last unpaired proton and neutron. So B5 is equal to AB delta A to the power Kp. Delta is equal to +1 for Z even, N even, that is capital A also even nuclei. Delta is equal to 0 for even odd nuclei. Delta is equal to -1 for odd nuclei. The value of the exponent Kp is determined from the experimental binding energy data. In the past, its value was often assumed to be -3/4. But modern experimental data indicate that a value of -half is nearer the mark. So now what is the final expression of semi-empirical mass formula? Binding energy is equal to AVA minus AS A to the power 2/3 minus AC Z Z minus 1 A to the power -1/3 minus A minus 2Z whole square A to the power -1 plus AP delta A to the power -half. Now delta +1 for even nuclei, delta 0 for even odd or odd even nuclei, and delta is equal to -1 for odd nuclei. Now we will see calculation of binding energy by an example. Example 1. Using liquid drop model, find the most stable isobar for A, mass number 27. The values of AA and AC are given. So first we will write down the expression of binding energy with the help of semi-empirical mass formula. As it is told about the most stable isobar, so we will make del B by del Z 0. So we will make the differentiation of del B by del Z. The first term, second term will not contribute anything. Third and fourth term there is a Z, and last term there is no Z. So only third and fourth term will be written over here. We will differentiate and we will make it 0. Then we will find Z value this much. Now substitute all the values of AA, AC, and we will get finally Z is equal to, atomic number is equal to 12.6, which is approximately the 13. So we will make the isobar for A is equal to 27 and Z is equal to 13. Another simple example, example 2. Calculate the binding energy of calcium. What is the percentage discrepancy between this value and actual value? Some values of AB, AS, AC, AA and AP are given over here. So we will calculate binding energy by two ways. The first one by the mass defect, and we will find the actual binding energy is coming as minus 342.05 mega electron volt. But by using semi-empirical mass formula, when we put all the values, we will find the value is coming 343.59 mega electron volt. So how much is the difference? Divided by 342.05 is equal to 0.5%. It is the discrepancy. Now there are some practice questions. Numerical. Which isobars of A is equal to 75 does the liquid drop model suggest to be the most stable nucleus? So some values are given. We have to calculate according to the example 1. Second question, derive the expression for semi-empirical mass formula. Third, calculate the contribution of Coulomb energy and surface energy terms for uranium nucleus. As a reference, I have taken the help of Introductory Nuclear Physics by Crane, Concepts of Nuclear Physics by Cohen, Introduction to Nuclear and Particle Physics by E.K. Mittal, and few slide shares.